Okay, so in this talk, I will explain a result about expansion in the so-called Grassmann graph. I will define what this graph is. So I made one small change to the title. We will be concerned about non-fully expanding sets in the Grassmann graph. So again, I will clarify what this means. And this is a sequence of joint works with various subsets of these authors: Irit Dinur, Guy Kindler, Dor Minzer, Dana Moshkowitz, and Muli Safra. And this result is used to prove the 2-to-2 games conjecture or theorem. So just to quickly recall, 2-to-2 games was the following problem. And if you want me to write bigger, just let me know. So this is a problem where you have a bunch of variables, and the variables are over an additive group. So let's in this talk, the additive group will be F2 to the L. This is a standard field with 2 elements, and L is thought of as a constant. So it's alphabet of size 2 to the L. And we have n variables and equations. Each equation looks like, say, xi minus xj is either Cij or Bij, right, within this additive group. Okay. And the goal is to find assignment to the variables which satisfies as many constraints as possible. And the theorem is the following, that for every small constant epsilon, there is a large enough integer L such that it's NP hard to distinguish whether such a system is almost satisfiable or not satisfiable at all. Okay. So specifically for every epsilon, there is L such that it's NP hard to distinguish if such an instance is at least 1 minus epsilon satisfiable, meaning there is an assignment which satisfies 1 minus epsilon fraction of the constraints, or is at most epsilon satisfiable, meaning any assignment can satisfy at most epsilon fraction of the constraints. So you can think of it as two related questions. Either that I give you an instance, I tell you that it's either 1 minus epsilon satisfiable or epsilon, at most epsilon satisfiable, and your goal is to decide which case happens to be the case. Or you can think of it as a computational problem where I give you an instance, I promise you that there is 1 minus epsilon satisfiable, and you are algorithmically trying to come up with an assignment which is as good as possible. In that case, it would be NP hard to find one which is even epsilon satisfiable. And these two different problems, they are really or morally the same. At least in computer science, we think of these two problems as being pretty much the same. Okay. So that's the theorem. And to tie it with what we did in the first talk, it's proved using the following scheme, which I tried to sketch. We really want to show that this problem is hard. This is 2-to-2 games. And here the variables are over this group F2 to the L, and the constraints are of this type. Xi minus xj is either Bij or Cij. And to show that this is hard, the only thing we can do is give a reduction. And in this case, the reduction happens to be from a problem called 3-lin. And this is already known to be hard. And this is a problem where the variables are over just GF2, 0, 1 variables, and the constraints are linear equations, mod 2. And each equation has exactly 3 variables. So it's a problem where each equation looks like this: yi plus yj plus yk is equal to either 0 or 1, depending on the equation. Okay. And again, the goal is the same, to find assignments satisfying as many equations as possible. And this is well known to be hard. So here it's known that if I give you a system and I tell you that it's 1 minus epsilon satisfiable, then of course you can take a random assignment. To each variable assign 0 or 1 at random, you satisfy half of the equations. And it's known that you cannot, it's NP hard to find assignments which are strictly better than just 1/2. So this is actually a well-known result in computer science. So you take instance of 3-lane problem and somehow use a reduction to construct an instance of this 2-to-2 games problem. So I'm not going to describe the reduction because it involves aspects which are probably more appreciated by computer scientists than pure mathematicians. So I will focus on the pure mathematical aspect, which is this theorem about expansion in Grassmann graph. So let's call it Grassmann expansion theorem. And I will show that this implies what we will call linearity testing theorem. So I will state both these theorems, even show the implication from this to this, and then this is the theorem which is in the end plugged into showing the correctness of this reduction, and that part I won't do. And towards the end, I will try to at least give a very, very preliminary sketch of how this theorem is proved. Okay. So that's roughly the plan. So we'll start by describing what the Grassmann expansion theorem is. So we'll have to define the Grassmann graph. So let L and N be integers such that L is a large integer, and after you have fixed L, N is a sufficiently even larger integer. And the space of consideration would be the n-dimensional space over F2. The vertices of the Grassmann graph, so let's call this graph GBE. So the vertices will be all subspaces of dimension little l. So subspaces L whose dimension is little l, right? So here is a vertex, maybe here is another vertex, L, L prime, and so on. And the edges of this graph will be pairs of subspaces which intersect to the maximum extent. So if you have two subspaces of dimension L, the maximum possible intersection is L minus 1 dimensional. So if at that intersection you connect them on edge such that dimension of the intersection is L minus 1. Okay, so this is the graph of concern for the rest of the talk. And we want to study expansion of sets in this graph. So just to make it concrete, expansion of a set, so S will be a subset of vertices. Expansion of a set is pick a random vertex from this set, take a random edge leaving that vertex, and it's the probability that you end up outside the set. Right? So this is the probability that if I take a random vertex L in the set, take a random edge L, L prime going out of L, then is the probability that L prime lands up outside. Right? So, and clearly this quantity is a number between 0 and 1. Okay. So this is expansion of a set. Now the following is quite clear. So suppose I take a set which is of size delta times the total number of vertices, where think of delta as extremely, extremely small. And if this set was random, right? A random subset of size delta times the set of vertices, then what would be its expansion? Its expansion would be extremely close to 1, okay? Because if it's a random set of size delta, the fraction of edges which end up inside would be delta squared, right? Which is completely negligible relative to the edges which are actually incident on that set, right? So if it's a random set of small size, then expansion would be very close to 1 with high probability over the choice of the set. And the question of interest is this always the case? In the sense that if I have a set of small size, is it necessarily the case that its expansion is close to 1? And if the expansion is close to 1, that's what I mean by saying near full expansion. Okay? So is the question clear? And the answer turns out to be no. Meaning there are sets which are not expanding. In fact, there are sets whose expansion is 1/2. And I will spend some time in describing these sets. These sets are quite canonical in nature. So there are canonical sets whose expansion is 1/2. There are those whose expansion is 3/4, 7/8, 15/16, so on and so forth. But all of them strictly bounded away from 1. So what are these sets? These sets are of two kinds. We call them zoom-in sets and zoom-out sets. So what are zoom-in sets? These are the sets of the following kind. In this space, fix some particular specific point, x, a non-zero point, and take all subspaces L which contain that. Okay? And that's a set of vertices in the Grassmann graph. So fix x which is non-zero, and let S sub x be all L which contain that point. So what would be the expansion of this set? Okay. So this I claim is essentially 1/2, because pick a vertex in this set, meaning a subspace L which contains x, and now try to move from L to some L prime such that L intersection L prime has dimension little l minus 1. So if you move to L prime, what's the chance that x would still be included? Right, that would be 1/2, because the intersection of L and L prime, quantitatively, it constitutes half of the points of L. So half of the points are retained and half of the points are thrown out. So x is retained with probability 1/2. So the and with probability 1/2, x will be thrown out. So the expansion of this set is 1/2. Okay. So this is, I hope, is completely clear. Now you can extend this example a little bit. You can take some small number of points, x1, x2 up to x sub a. Think of a as small constant like 5, and take all L which contain all these x1 up to xa, and the expansion of this set would be, by the same argument, 1 minus 1/2 to the a, because if you have a space L which contains all these points, and then you try to move to L prime, the probability is 1/2 to the a that all these points would still be contained in L prime, right? So the expansion would be 1 minus 1/2 to the a, and for small a, this is thought of as having expansion strictly bounded away from 1, below 1. Okay? So these are the sets which we'll call zoom-in sets. Now there is essentially some sort of dual of this, which we'll call zoom-out sets. Right. So yeah. So I should have made it clear. There is a small additive term which is of the order of 2 to the minus L. So those the small ones I'm going to ignore. Right. You're right. The zoom-out sets. These are the sets where in the whole space you take a subspace W of codimension 1. So you could think of it as picking a vector y, and it's the space which is orthogonal to y. The inner product being the standard inner product. So these are the sets of the following type. You pick a y, non-zero y, and take a set called S sub y orthogonal. So these are all L for which L is orthogonal to y. Or it's same as saying L is content in W in this picture. For the same reason, expansion of this is 1/2. Right? Because if L is orthogonal to y, and you try to move from L to L prime. To move from L to L prime, you really have to take one more independent point, right? Throw out one independent point from L and take another one from outside. And the probability that that new independent point still remains orthogonal to y is 1/2. So with probability half you stay inside, with probability half you jump outside. So these are the sets with expansion half. Again, you can call a set, extend this example to some y1, y2 up to y sub b for some small b. These will be all L, which are orthogonal to all of these, y1 through yb. And the expansion of this set would be 1 over 2 to the b. Sorry. Yeah. 1 minus 1 over 2 to the b. Now you can also combine the zoom in with zoom outs. You can do both, right? So in general, you can define, and these will be called the canonical sets. A canonical set is of the type that it contains some A points, and these are thought of as linearly independent. It contains some A specific points and orthogonal to some B specific points. And the expansion of this would be 1 minus 1 over 2 to the A plus B. Okay. And these are the canonical sets. Just to recap the picture we have seen so far, this is the Grassmann graph. And inside this, there are these canonical sets whose expansion is strictly below 1. And pretty much, these are the sets whose expansion is strictly less than 1. But you can do a little bit more than this. You can take a canonical set, and inside that, you can set a subset of constant density, and that still has expansion below 1. This is very, very easy, so I'm not going to prove this. So if you take a subset S of a canonical set whose density inside that is epsilon, then its expansion is at most 1 minus epsilon times whatever corresponds to that canonical set to the A plus B. Okay. And this theorem, which I call Grassmann expansion theorem, it states that that's it. This has a converse in the sense that any set whose expansion is strictly below 1 is necessarily of this kind. Okay. That's the theorem. So let me state the theorem. So for every constant alpha, there is a epsilon and an integer r, such that the following happens. If an expansion of set is strictly below 1, then what can you say? What we are going to say is that in this case, there is some canonical set inside of which the given set has constant density. Okay. Then there exists subspace A of dimension little a and subspace W of codimension little b. And then the canonical set would be all L, which are sandwiched between A and W. It looks slightly different from this definition, but it's really the same. You're supposed to contain the space spanned by these, which I'm calling capital A, and you're supposed to be contained in the space orthogonal to these guys, which I'm calling capital W. Right? So these are all vertices L of the Grassmann graph, which are sandwiched between A and W. So there is a canonical set S superscript can such that the given set S has constant density inside. Right, and then this A plus B is at most equal to R. So such that that's the theorem. So is this clear? And from this, you can even derive a full structural result. So this is only saying that the given set has constant density inside some canonical set. Now you can take that constant density set, throw it out, and repeat the argument. And once you repeat enough number of times, in fact, you will cover a constant proportion or a constant fraction of the original set. Okay? So in the end, what you can derive is that the set is constant fraction of the set is can be written as disjoint unions of sets, each of them having constant density inside some canonical set. Right? So you can immediately get a complete structure theorem from this. So that's a minor issue or minor observation, but this is really the result. And from this, we want to derive what I will describe as the linearity testing theorem, which is then really used in the reduction. Right. So that's what I meant to say, that once you, of course, the set S has lot of it outside of that canonical set, but you can repeat this argument, meaning whatever is inside that canonical set, throw it out. Now the remaining set still has to have low expansion, so it's going to again be dense somewhere. So take that out, throw it out, just keep repeating, and you will cover constant fraction of it in the end. Right. So in that sense, it gives a complete characterization of the original set. Right. So now what is this linearity testing problem? This is the kind of problem which computer scientists are fond of. So suppose there is a function f on the global space which is linear. And now, for fun, I do the following. I write down the restriction of that function to every subspace L of dimension little l. Okay? So write down, and we'll call that a table. So write down the following table, that this is capital F. For every subspace L of dimension little l, write down restriction of this function, the global function, to space L. Now this is a linear function on little l dimensional space. So this answer has only 2 to the L possibilities. Right? You can describe it using 2 to the L symbols from alphabet of size. Right? Now, the linearity testing question asks the following. So what if I only gave you this table capital F, meaning for every L dimensional space capital L, I gave you some linear function, okay? Now, can you somehow check that these, whatever is given to you, actually corresponds to some global linear function, right? Restrictions of some global linear function, okay? So it's some kind of inverse problem. Given a table F, I somehow want to check or verify that it corresponds to restrictions of some global linear function. Okay? And we want to test this using a test. Is that clear? Now here is a proposed test. If it was indeed the case that these were restrictions of a global linear function, the following must happen, that if there are subspaces L, L prime which intersect, in particular let's say they intersect in one dimension less, then the linear function on L must agree with linear function on L prime on the intersection. So f of L and f of L prime should agree on L intersection L prime. Okay? And now I want to view it as a probabilistic test where I pick an L L prime, the pair L L prime at random, right, whose intersection is little l minus 1, and then I accept or reject depending on whether, so accept if and only if whatever ought to be true is true. Okay? So does this make sense? So this is right, and this is called probabilistic testing, which is quite popular and useful in computer science. Now two things are clear. So the firstly that this is what is called 2-2-2 test, meaning if I have these two answers, each answer is a symbol from alphabet of size 2 to the L, but if the test were to accept for any answer here, there are exactly two answers here which are acceptable, because once you have restriction to L, it purely determines, completely determines the function on the intersection, and then to extend it to L prime, there are only two more possibilities. The functions have to be linear, right? So given an answer to L, there are exactly two answers to L prime for which I could possibly accept, and vice versa. Okay? And this, in the end, somehow is going to correspond to the proof of the 2-2-2 games theorem, where the constraints are these 2-2-2 constraints. Okay? So just to somehow connect this whole this business with the business of actually constructing reductions. Also, this has what is called perfect completeness, meaning if everything is, yeah. Right. So this is the input for every. There is no little f as far as the input is concerned. Exactly. Exactly. Right. So input is just this, right? And we want to somehow determine whether it is actually compatible with some global linear function. And of course, you can determine this by reading all these guys for every L. And of course, you can do it. But somehow, the goal is to check by looking only at, in this case, two samples. Okay? So I pick two samples, LL prime, whose intersection is L minus 1, and check if they agree. Okay? And this test clearly has what is called perfect completeness, in the sense that if what is given, the input, is indeed compatible with some global linear function, this test will accept with probability 1. So that's clear. So the interesting question is the reverse. What can you say if this test accepted with probability, let's say 0.1, meaning on 10% of the pairs LL prime, you had the agreement. Does this imply some kind of global agreement with some global linear function? Okay, so that's really the question. So yeah, I don't know which one to use. Right. So the question is, suppose we have the following property that for a random pair LL prime, what's given as input agrees on, let's say, some alpha fraction of the pairs, then is it the case that there is some global linear function for which what's given as input is consistent with that global linear function. But of course, you cannot expect complete consistency, right? So I want consistency on some good fraction of the spaces. Okay, so this is the question. Okay. Makes sense. I mean, if you're a computer scientist, you have seen like 20 theorems like this, where the answer is always yes. But in this case, the answer turns out to be no. Yeah, so here the answer is no. And the reason precisely is that in this Grassmann graph, there are these canonical sets which are non-expanding. Okay. So here is the reason. What I could do as a counterexample is as follows. Let's say I take a point x and take this set, canonical set Sx, which is all spaces which passing through x. Then I go ahead and pick another point y and take the set Sy and just keep doing this, right? For z, there is another set called Sz, and these sets are going to be more or less disjoint. So let's just assume these are disjoint. And I picked sufficiently many points such that, let's say I covered some constant fraction of the spaces L. Okay. Now, for each x, what I will do is I will take that set Sx, and to all spaces which contain x, I assign them according to some global linear function, call it f1. Okay. So for each L here, I will write down the answer as f1 restricted to L. But then for different y, everything which is in Sy, I do it according to some completely different function, f2. And for some other third z, I do it completely using completely different function f3, and so on and so forth. Okay. So clearly, there is no way to come up with some f which works on all of them, right? On the other hand, it does satisfy this for constant fraction of pairs. What I assigned, it does lead to agreements on pairs, because each of these sets has expansion 1/2. So half of the edges incident on that set lie inside, and all the edges which are inside that set, I did according to some global function f1. So there will be agreement on all those edges which are inside the set S sub x. And similarly, everything which is all edges which are pairs which are inside S sub y, I got the agreement, so on and so forth, right? So so this gives you a construction, a counterexample, meaning a construction of such a table F, which is consistent on some constant fraction of pairs, but there is no global function which can be consistent. Okay, So therefore, the answer is no. However, there is a way to save this or salvage this counterexample. Now, in this case, I do I do the salvation cheaply. Suppose I am allowed to pick a specific point, let's say x, and say okay, forget about everything. Let me only consider or zoom in into spaces capital L which pass through X. Okay, so I will focus my attention only to those spaces. In that case, I mean, just by design, the way this is counterexample is constructed, now there is indeed a global function called f1, which is consistent with everything, right? So if I'm allowed to zoom in into one of these canonical sets, at least in this counterexample, the situation is saved. Okay? And this is the linearity testing theorem, that this can always be done. That you can always zoom into some canonical set and save the day. Meaning on that canonical set, you will have a very good agreement with a global linear function. Okay? So that's the result. So this is the theorem that if the probability of this agreement is at least, let's say, alpha, then there exists again this space A and W of dimension little a, codimension little b, a plus b is at most r. Well, I guess I have to put some quantifiers for every alpha. There is epsilon and r for which the following holds. If the agreement is alpha, then on some, so there exists this zoom in and zoom out and a global function f such that it is indeed the case that if I only now consider those L which are sandwiched between A and W, on those, what is the input? This is what is given to me. It is indeed consistent with some global linear function on epsilon fraction of the spaces. Okay, so that's this is the theorem. Right. So how much time? Oh, okay. So yeah. So I guess I don't really have time to get into or even start the proof of this Grassmann expansion theorem. So what I will do is this is a very quick but nice proof by Barak, Kothari, and Steurer, which shows that if you have this result about expansion, you almost immediately you get this result about linearity testing. Okay, so I can do this. It's cute, nice proof. Right. So what I want to show is this theorem, right, implies this. Right, this one. So we start with this this given table, which has agreement of alpha And somehow we want to first of all find this canonical set and then find this function f which has the agreement. Now this is actually quite strange proof really, in the sense that if you are a coding theorist, at some level this really amounts to decoding a code, decoding a received word which is corrupted. So it's a decoding procedure. And then in general, decoding is a rather non-trivial task. So you have to do something clever to decode received words. But here, the decoding is simply, or at least on the surface, it appears as if you take a random word, a random code word, and declare it to be the decoding. So for a coding theorist, this is going to look completely ridiculous, but this is what works in this case. So, but somewhat indirectly. So what we are going to do is, this function f will actually be a completely random function. So pick a random function f, but then the set, the canonical set will be defined in a somewhat little clever manner. Okay, but this function f itself is just chosen at random, and this is really what amounts to decoding from a coding theoretic sense. So this is a proof by Barak, Kothari, and Steurer. So pick a random function. Let's call it g. It's linear. And now look at the set S sub g, and this is the set of those spaces L on which g agrees with the input. Okay, so I first pick a random linear function and then check wherever it agreed with what is given to me. Now, what is the expected size of this set relative to the size of the whole graph? So I claim that the expected size is 2 to the minus L because for every specific space capital L, this is already given to me, and then g is completely random function, so its restriction to L is also a random linear function. So it agrees with something which is already specific to me, given it's 2 to the minus L. So I expect this set to be of size 2 to the minus L. Now secondly, we will show that this set has lots of edges inside. So expected fraction of edges inside the set. Okay, so how much is that? So suppose LL prime is an edge, and these answers FL and FL prime, these are given as linear functions on L and L prime. Now I know that for alpha fraction of the edges, these given answers they agree, right, on the intersection space L intersect L prime. So I'm only going to look at those edges for which there is agreement. Now whenever there is an agreement, I claim that this random process, the probability that the vertex L ends up inside this set S sub g, that's clearly 2 to the minus L. But once it's inside the set, this function f of L agreed with this global linear function, and then it will also agree with this function FL prime with probability another half, because that's only one extra degree of freedom, right? So once this vertex is in, this other vertex is also in with probability 1/2, and this happens for alpha fraction of the edges of the graph. So the expected number of edges, fraction of edges inside this is 2 to the minus L times alpha over 2. Okay, right. Now this is in expectation, but that's a minor point. You can always very easily show that there is some choice of function g. So there is some choice of g, call it g star, such that the following holds. So this is a set whose size is 2 to the minus L, and the fraction of edges inside is the size times alpha over 2. So its expansion is strictly less than 1 by the amount alpha over 2. So its expansion is So phi of the expansion of that set is at most 1 minus alpha over 2, and then we are done because this is a set on which expansion is strictly below 1, and therefore once I'm allowed to zoom into some canonical set, its density becomes a constant, right? So this implies that there exists some canonical set such that this set SG star has density at least epsilon inside the canonical set. And if this canonical set is, let's say, represented by these spaces A and W, it's basically same as stating that on L's which are sandwiched between A and W, the given table agrees with this G star, okay, on at least epsilon fraction of the spaces. That's the density inside that canonical set. And that was the conclusion one was aiming for. Okay. So it's very quick, easy proof. Right. Yeah, and then I will just say the following, that if you want to prove this theorem, then it's spectral analysis on the Grassmann graph. For the Grassmann graph, it's somewhat studied graph. It's in the family of what are called distance regular graphs. In particular, its eigenvalues are all known or were known, and these are essentially decreasing powers of 2, 1 half, 1 quarter, 1/4, and so on. So you start with a set whose expansion is strictly below 1, and show that this statement, that expansion being strictly below 1, is pretty much equivalent to saying that the indicator function of that set, you look at its Fourier spectrum. Fourier spectrum amounts to partitioning the function into levels, and these levels are eigenspaces, different eigenspaces corresponding to eigenvalue which is 1, then 1 half, 1/4, so on and so forth. So there are these different levels of eigenspaces, and a set with low expansion amounts to having significant Fourier weight on some low level. Okay. Right, and then you start from there and do a bunch of gory things, and at least eventually we managed to do this. So in the article which is written for this conference, there is a proof in some toy case when there is some significant Fourier mass at level 1. That you could take a look if this interests you. But then working with higher Fourier levels, that's much messier. Right, that's it. Yes. Yeah, over finite fields, it should be the same. Yeah. Though we don't do it because actually for us, looking at the application, the result will get worse. So the question is, we have this reduction, let's say from 3-sat to these 2-to-2 games. Now I can take a random instance of 3-sat, it's hard, and map it via this reduction, and I will get a distribution over instances of this problem. Is this distribution easy to describe? I don't think so. It's a reduction, but the reduction is quite concrete. So you can take the reduction and whatever it gives. But in the end, this distribution, as I tried to make a point in the first lecture, that we couldn't have come up with this distribution without knowing the reduction. Right. So it's not natural in that sense. You couldn't have thought of it a priori. Whether it might have applications to UGC, well, in some sense, yes. I mean, it does suggest what kind of graphs that should appear as hard instances of the unique games problem.